to my presentation on Beyond Buzzword Bingo on the subject of data science, and the question this addresses is, why is it hard? Up to now, I've been telling you that AI is actually based on relatively simple principles. So that begs the question, what is the waiting for? Well, actually, believe it or not, data science is hard. It's hard for a variety of reasons. Method and maths, stuff around data, and actually humans make it hard. So I will be going all over these three factors, starting with methods and math. As a data scientist, making an artificial intelligence model, that actually turns out to be a balancing act. Tuning the model, as it is called in professional terms, you'll find that a data scientist will spend around 40% of his or her time actually getting all of this stuff right. So what do we need to balance? Well, first of all, the so-called bias-variance trade-off. And that's really the trade-off between a simple model and a complex model. If it's a high bias model, then it will be too simple. And if it's a high variance model, it will be too complex. Neither is good. You need to strike the balance. A high bias model, which is too simple, it generalizes well, but in general is not very accurate. On the opposite side, a high variance model will show to be very accurate, but doesn't generalize. So let's get a couple of examples out. Remember that earlier in the presentations we did something around playing tennis. I had collected all this data, but you can actually apply a very simple model to it. You can go out to a bookstore, get a farmer's almanac, and actually look up what's the weather forecast for the month of July. And it will actually tell you that generally in the Netherlands it rains. So a simple model would be, which is very consistent but not very accurate, it rains, so don't play tennis. The opposite side is a too complex model. A good example of that is what I actually did in the example, namely noting down the data and actually coming up with, or have the model come up with, a decision tree. And that is actually very accurate model, but it is only accurate for me, for just in my simple case. Somebody else may actually have a very different model. And you need to strike a balance between this very precise and overly complex model versus being way too simple. Now, luckily here in this case, we've got something called rain radar, buienradar in Dutch, which will tell me where it will rain, so I can forecast. So balancing between too simple and too complex is one. Next one would be the precision recall trade-off, and that is the trade-off between, if you will, usefulness and the completeness of the results. And that in fact is actually the balancing of the false positives versus the false negatives. Example of that is, here you have a fire alarm. If the alarm is too sensitive, which in sensitivity is another word for precision, you'll find it goes off too often and people will start ignoring it. So you don't want it to be too precise. You want it to be right. Opposite side is, for instance, cancer screening. Breast cancer for women in the Netherlands, bowel cancer for males in the Netherlands. But you don't want to miss have too many false negatives in the sense that you actually misdiagnose. So you need to strike a balance between the two. Again, a balancing act. In later clips of this video, I'll go into how you would actually tune this model and what the options are to reach that. But as said, you actually spend significant time on reaching the correct balance. Next would be something called the curse of dimensionality. Now, this is a problem that is particularly geared towards machine learning, the latest neural network developments make it a little less of an issue, but particularly in machine learning algorithms, this is an issue. And that is really the problem between too few variables and too many variables. So to say come up with an example, let's say we've got a coin here, and if I put that coin somewhere along this line, my question would be, would you find it? Well, most people will answer, well, depending on how long the line is, I would. And clearly so. Now, a line is clearly a one-dimensional variable. If we put in a two-dimensional space, for instance, two soccer pitches, and I put the same coin on there, and I ask the question, would you find it? You will already say, well, but ultimately you would agree that very likely it may take a while, but you will find it. Now suppose we put it in a three-dimensional space, like this building, which happens to be the head office of my bank. You can even take the biggest building in the world, and if we put that coin somewhere, then the question would be, would you find it? I'm sure that you'll get doubts now. And that is what this cursor dimensionality is about. It is difficult to find sparse patterns in high dimensional space. And every variable actually is a dimension. So suppose I ask you to look for this euro, but this building is full of also pound coins and dollar coins and yen coins and Swedish kroner coins and all kinds of coins, it would already be harder, particularly if there is only one of these coins around in this entire building. And then it becomes actually very, very, very hard. So you need to find the level of noise from too many dimensions with too few that you don't actually get sufficient signal. And there you have it. And next up is data, but that will be in my next clip. Thank you.